Okay, so we've been written down this Landau-Lifshitz formulation of Einstein's equations. We've imposed Lorentz gauge and arrived at an equation for this field H alpha beta, which we can relate to the space-time metric at the end of the day, in terms of it's a flat space-time wave equation with a source that consists of matter, stress energy tensor, the Landau-Lifshitz pseudo-tensor, and this little extra piece of harmonic pseudo-tensor, which basically has two terms. Remember that the Landau-Lifshitz pseudo-tensor is also quadratic in first derivatives of H, quadratic and higher in first derivatives of H. Or it's quadratic in first derivatives, but there are higher terms in H. So it could be like H, grad H, and so on. But nothing linear in H, that's for sure. And then finally we have our equation of motion, which we can use either in this divergence form, just the divergence of the right-hand side vanishes, or if you want to just wish to use the covariant version, plug in the matter variables in the metric at the end, you could get some motion that way. Okay, so how do we sort of approach solving this equation? So the idea is to first assume that we're going to consider situations where, at least for a large region of space-time, this h, this deviation from a flat space-time, is small in some sense. I'm not going to totally make any rigorous statement of what I mean by small, but you sort of get the idea of what small is, right? It's just small. And the idea is to iterate these equations. And there are two ways we can write down this equation. We can write it as a wave equation, or we can actually integrate the wave equation, because we know how to do that. You know what the green function is for the flat space-time diversion. We know that the solution, or as an integral, h is equal to an integral of the source, alpha beta, over all space, divided by x minus x prime. That's what we had in Newtonian theory. That was the Newtonian potential of a source. In Newtonian theory, everything was evaluated at the same time. In Newtonian theory, time is absolute, it's just one time. But now, because of the flat space-time operator, the time at which you evaluate the source is the current time, the time where you're looking at the field, minus the distance to the source divided by the speed value. This is retarded time. You evaluate the behavior of the source at a time earlier than where you're looking, earlier by the distance between you and the source divided by c. So this is the standard retarded solution of the wave equation. The idea is that with h small, we can take this right-hand side, for example, and start with h equals 0. That would be our lowest approximation, just flat space-time, no gravity at all. And plug h equals 0 into the right-hand side, and then solve for that, either this or directly using this integral. So we get the first iteration, and the first order solution, h1. And then take that solution and plug it back into the right-hand side. Remember, the metric appears everywhere. It appears in T alpha beta, it appears in Landau-Lifshitz, etc. Plug h1 back into here, and calculate the next iteration, h2, and so on. So at each order, you have the nth iteration of h, plugged into the right-hand side, do the integral, and get the n plus 1 iteration, and keep going until you have the accuracy you want, or until you're dead, or whatever you need to do. Okay. And you can see that this yields an expansion in powers of Newton's constant g, because at the lowest order, when you have h equals 0, the h that you get is proportional to g, because that's Newton's constant that appears here. So when you plug that in here, there'll be g's within here, but then there's another g. So this is going to be terms that are order g squared, and so on. So you get this sequence in powers of g, and this is where this is called a post-Newtonian expansion. And this is an approach that was developed in France by Thibaut d'Amour and Luc Blanchet, building on earlier work by other people. And that's where this terminology comes from. It's really an expansion in powers of g that you get by just going keep cycling through with higher order solutions for H. Once you get the iteration that you want, you then take that field, plug it into this divergence of the right-hand side object, this energy momentum pseudo-tensor that includes Lambda-Lipschitz and the harmonic pseudo-tensor. You plug it into here, set it equals 0, take the divergence, set that equals 0, and that gives you the equations of motion that tells you how the matter behaves, what the variables are, and then you can take those and plug them into H, which is just a functional of those variables, and you plug it up with your field in space-time. Okay? So it really relies upon this idea that the field, that we're really doing a kind of weak field expansion, but we can carry it systematically to higher and higher order. And one reason why this really works well is that if you remember, this top consists of matter and these two pseudo-tensors, the Landau-Lipschitz one and this harmonic one. And those two pseudo-tensors were all quadratic in H. So if H is small, then these things are going to be order H squared. So you're adding corrections that are even doubly small. Okay? You find H, set H equals 0, you find H1, plug it back in, but H1 is going to be squared in those two pseudo-tensors. It won't be squared in the matter part, but then there's a rho in the matter part, and that, of course, is the source of the potential we're trying to derive. So these two extra pseudo-tensor pieces kind of are allow you to think about it, the idea that the sequence might give a good approximation to a solution as you go to higher and higher order. So it's really important that those two pseudo-tensors be quadratic and higher in powers of H. So what does this retarded integral look like? You have this retarded integral, it's sort of written down mathematically, but what does it sort of mean pictorially, and how can we kind of sort out how to carry out such an integral when we have, say, a source, a material source of our gravity, such as a binary star system, and gravity itself. So I want to simplify this discussion by focusing just on a simple wave equation. Let's just throw away all the tensors just to clean things up. I just want to imagine a flat space-time wave equation for a field psi with a source mu, but this source mu can contain psi itself. It could contain a bit that depends just on the matter, but it can also contain psi itself. So we have our integral over the source, integrated over all space, divided by the distance x1. And here we want to do something that you do, you're very familiar with from electrodynamics. We want to take our world and divide it up into two regions. We imagine that the source, this is a space-time diagram, we imagine that the source is confined to some region, a little narrow tube here that goes forward in time. Two stars orbiting each other forward in time, maybe just a star sitting there. So our material is in some very narrow world tube down here. These could be in these would be the charges that are generating the electromagnetic field. And then we want to divide space, the spatial part of this space-time diagram, into two regions. One region called N that is where the distance from the source is small compared to a radius r. That radius r is of order of the gravitational wavelength of the system if it were emitting gravitational waves. Roughly speaking, that means this radius r is something that scales as the size of the source, the physical extent of the material part, divided by a characteristic velocity of the source. Right? So this SORB is like the period of motion of whatever the source is, and that period then is proportional to the wavelength. I think I said C equal to 1 in the spaceship. So this is like a wavelength of radiation. Of course, if V is small, when we're going to typically assume slow-moving systems, if V is small compared to the speed of light, then R will be large compared to the physical size of the source. So the wavelength of radiation is very long compared to the size of the actual source. So this will describe a world tube of radius r. This world tube then moves through space-time that way. That's the world tube d. And then, now, what is this retarded time? When I integrate this psi, I'm integrating over the source, not at a fixed time, but at a time that varies as I increase x prime, the distance of my integration point from the field point where I'm looking for the source. So when x prime is equal to x, that's, I'm evaluating the source at time t. But when x prime starts to go away from x, I have to evaluate it at an earlier time. And so what you see is you're evaluating the source along this surface, this cone, where as x goes away from, x prime goes away from x, t goes down by exactly the same amount divided by c, and so it's the surface of this cone. So it's a null cone with our field point at the vertex. So we're integrating mu over this surface. Call that c for the null cone. And it's a flat space-time null cone because our operator is the flat space-time operator. Well, this cone will intersect this world tube and at a surface that I call M. And that's what it's called M because this is the near zone. This is the region where R is small compared to the within one wavelength of the source, and then W is everywhere else on this null cone. So W is C minus this N. So of course, in this N we'll have a material source, but there'll also be source here, and of course there'll be source of our field at X generated by here in W. Because remember, mu, when we do our gravitational case, mu is not just the material source. It contains the Landau-Milstein pseudo-tensor, which is everywhere. Because H, it contains H itself, and H is everywhere in space-time. So this source does not have what mathematicians call compact support. In other words, it's beyond, it's more than something that exists in a finite region and then is zero everywhere. That's true in electrodynamics. You only have a source where there's charge. The electromagnetic field itself does not generate electromagnetic field. But in gravity, gravitational field has its own stress energy tensor. So, so this source mu does not have compact support. It exists everywhere in space-time. So this integral definitely has to be done over the full null cone, not just over the near zone, but also here. And we'll see as we go along, this will require rather different ways of trying to calculate, evaluate this integral for this source mu. At the end of the day, of course, and so what we're really going to do is to split this integral into two pieces, the integral over the past null cone, C, into an integral over this little bit, this little patch, psi n, plus the integral over the rest, psi l. That then will be our solution to this wave equation. In each region, for each of these, we do the calculations slightly differently. So let's first look at the near zone part, psi n. This is the integral over this surface n of our source mu. But inside this zone, x prime, I'm assuming my center, center of my coordinates is at the source. So x prime is of some location in this region n. So there's, say, x prime here. We're assuming that this x prime is very small compared to the distance to our source out there in the wave zone. Okay, so x prime is very small compared to x. So let's just Taylor expand the x minus x prime that appears here. This is similar to what we did when we were talking about a slightly non-spherical body. We're looking at a point outside the body, we expand with respect to the x prime, which is inside. We do the same thing here. So it's just a Taylor expansion. We have sum over all L, minus 1 to the L factorial, x prime times a gradient of this thing evaluated at R. In other words, at x prime equals 0. So it's t minus r over r. Okay. and we take a gradient, L gradients of that thing with respect to R, and there are L exponents contracted with this, and that's our sum over all of L's. Okay. Same thing we did in Newtonian theory, except for the one wrinkle. In Newtonian theory, we just had a gradient of 1 over R. But now we have to also take a gradient with respect to the R that appears in this retarded time part. So it's a bit more messy than the simple Newtonian example. But once we make this Taylor expansion, we then just integrate over mu. So there's mu evaluated at retarded time. T cos t minus r, the distance of the source. We have x prime integrated over all space. And 1 over r is here. But then we have to take L gradients of that thing. And then we sum. And notice that I've now changed this integral from n, integral over m, to an integral over m. This m is a hypersurface at fixed retarded time. Remember, we're doing the integral over n. That's the integral we wanted to do. But we've converted it into an integral over this, m. It's fixed retarded time because tau is now fixed. It's just t minus the distance between our field point and the source. So time now is fixed in this interval. But now we have an infinite sequence of such integrals. So we've converted this integral here by kind of Taylor expanding the field here about this little surface there. And then that Taylor expansion has an infinite number of terms. This is just a multiple expansion that you do in EM, right? You want to calculate the field far away, you do a multiple expansion of the field here. You've seen this is in Jackson. Right? Nothing new here. It's all in Jackson. And in Jackson, you do this multiple expansion, and you just let this integral just go straight to infinity, and you get your solution to the field. But here we can't do that. The reason we can't do that is that mu does not have compact support. In E&M, mu only exists where there's a charge. Here it exists everywhere. And if we were to naively do this integral, or just to let m go all the way out to infinity at fixed time, we run into problems. Because at some point you're going to get a moment here that has a large number of L's. And you remember mu contains the Landau-Lifshitz pseudotensor, which is quadratic in gradients of h. And you say, okay, well, it falls off. It should vanish in infinity ultimately. It should fall off with r. Well, how fast does it fall off with r? Suppose if mu falls off as its gradient of h, so h is 1 over r, gradient is 1 over r squared. It's quadratic, so it's 1 over r to the fourth. So this falls off as 1 over r to the fourth. But d3x goes as r squared. So already a quadruple moment, we have an r to the fourth dr, and a 1 over r to the fourth, this integral would diverge. And if you go to higher order now, it's going to diverge like crazy. You don't care in E&M because mu is 0 once you're outside the source. But in gravity, you have to care because mu is everywhere. In the old days, we did these integrals, and everything diverged, and we took all the divergent terms and threw them under the rug. We didn't care about them. We argued they were divergent, but they were constant. Later on in the game, we know we're going to have to take maybe a time derivative of the field to get the energy flux or whatever, blah, blah, blah. We waved our arms and said, these divergences really don't matter. Okay. And that worked at very lowest order. It works for just the lowest order gravitational wave quadruple formula. It works for the first post-Newtonian corrections that Bob Whitehead and I did back in 1976. We threw many terms into the rug. The rug had this mound of this stuff shoved underneath it. But the answer was correct. I mean, it worked. But at higher orders, it doesn't work, and you just can't do it. So we have to think a little more carefully about it. We can't just take this integral over a fixed time and just extend it to spatial infinity. It won't work. So what we really have to do is think seriously about the fact that we have the rest of this null cone integrated. What we're really integrating over is a null cone. Here we approximated that piece of the null cone with a Taylor expansion expanding over here. But for this piece, maybe we just have to do something completely different. to do the rest of the integral. So this gives us psi n as a multiple expansion. What about psi of w, the rest? Well, here's how we do it. We take very seriously the fact that we're integrating over a null cone, and we change variables. We don't want to integrate over d3x, r, theta, and phi. Of course, integrate over theta and phi, that's fine, those are just angles, but we don't want to integrate over r, that's bad. Let's change the radial variables to something else. And here's the variable that we use. We change coordinates from r prime, theta prime, phi prime, that would be our original interval, to a different variable, u prime, theta prime, and phi prime, where u is defined to be, is related to these variables by this expression. This is a particular, I mean, you can pick, there's a particular way to picture this new variable, u prime. This expression, of course, describes our past null cone. Right? So for a given x, as you change x prime, whatever this object is, t will vary, and so that's our past null cone. This is also a null cone. It describes for a fixed u prime, it says that as you increase this thing, r prime must increase. So if you start here at r prime equals 0, if you let r prime increase, then whatever this is kind of a t prime, must increase as well. So this is a null cone. For a given u prime, this is a null cone that points to the future. It's coming from the origin, which is where our material source is. So this is a null cone pointing to the future, whereas this is the null cone pointing to the past of our field cone. And the place where these two things are equal, where this equals that, is just the intersection of those two null cones. So it's a kind of hypersurface here, a two-dimensional hypersurface. Right? It's the intersection of two three-dimensional hypersurfaces. So it's a two-dimensional hypersurface for a chosen value of u prime that is not constant time. Notice t here is less than t up here. Right? Take these two cones. This one is at our field point. This is at the center mass. This is the source. This is our gravitational wave detector. These cones are offset, so this is not the same time, but it's a fixed value of this u prime variable. So as you integrate over angles, for given u prime, you are integrating around this little region like this, but time is changing as you go around. But u prime is fixed. And then, to complete the integral, we have to integrate over all u prime, and for each u prime, of course, going into the infinite past, you keep integrating until this cone is just tangent to that cone. And further in the future, the cones don't intersect anymore. So that's just a mathematical transformation, but why should that be useful? Well, it's useful because out here in this region outside the near zone, the source is just a Landau-Lifshitz pseudotensor. There's no matter. Matters confined to that worldview. So it's all Landau-Lifshitz pseudotensor plus anharmonic pseudotensor. Those things are constructed from H. And H depends on retarded time. So this mu in this region where we want to integrate over is, you can actually show, is really a function of a retarded time tau prime, angles, and actually varies as 1 over r prime to some power n. It depends on what terms you're looking at, and so on. So that's why it makes sense to do your integration not in terms of some r prime, but in terms of some retarded lifetime that kind of matches the u that's here. So when you're integrating around this surface, you're fixing u prime, which means you're fixing this, and so you're just integrating over the angular dependence of this Landau-Lifshitz stuff. After you do that, then you integrate over this guy from minus infinity until the two cones are tangent to each other. I'll show a picture of this these steps in the next slide. So how would this work in practice? So here, this is what psi will look like when we make this coordinate transformation. This is the source, f, which now depends on this retarded time variable, u prime, theta prime, phi prime. This is our source. Maybe I should have had mu. I had mu earlier, so I made this mu. So there's our source. There's 1 over r to the, right? That's the f that's here. So this is what I characterize mu. So there's f, there's r to some power. But r itself is now a function of u prime, theta prime, phi prime. Write down that function directly. We integrate over solid angles. And there's a kind of solid angle piece there that comes out of the coordinate transformation, the Jacobian of the transformation. And then you have to integrate over mu prime. And that integration over mu, so that sequence of integrations looks something like this. Pick some mu prime, this one, so this future cone looks like this. Integrate over this curve, looking all the way around the backside, for one value of mu prime. So you do this integral for one value of mu prime. Then pick a later value and do the integral, integrating over mu from this one up to this one. Now, however, when you do the integral over angles, you see that this intersection between the two cones intersects the near zone. So it goes here, around the backside, and comes here and stops. We don't want to integrate in the near zone. We've already done that problem. So we only integrate around here, the backside, and stop there. And that's another u prime. Remember, keep integrating over all these u primes. The final piece of the integral comes when these two things are tangent. U prime is equal to u, and there's just a little integral from the upper edge of this near zone up to the field point. Integrate u along that little line. So this integral then goes from the infinite past, when this light cone is down there in the infinite past, intersecting way out there somewhere, and then you just integrate all the way up, terminating at this value where u prime is equal to u, which is just t minus r. Now the point is that when we did this multiple expansion in the near zone, I said we're only going to integrate over m, over this region. You might imagine that that integral might depend on the value of the radius that you've chosen for the boundary between the two zones. Right? I mean, it's a finite integral, and this integral might depend on the value of that curly r that we picked. And in fact, it will, it does, and you keep all those effects, all those terms. You might also imagine that this integral, once this thing starts to intersect, that parts of this integral might depend on r because you've terminated at the boundary of this near zone. And indeed it does. This integral also depends on this curly r, the radius of the near zone. But the sum of the two cannot depend on r. First of all, because I chose r to be completely arbitrary. It's a fictitious boundary. I chose it to be one characteristic wavelength. I could have chosen it to be two characteristic wavelengths. The answer surely cannot depend on where I chose this artificial boundary between two intervals. So the answer can't depend on r directly. And in fact, you can show, when you actually work this through and understand the nature of the behavior of this thing, you can show that all the terms from this integral that depend explicitly on r exactly cancel all the terms from this integral that depend explicitly on r. And it's true of sort of all Post-Newtonian orders. I mean, you can show explicitly that there's a remarkable cancellation, as there must be between these effects. But this cancellation is nice. The fact that the final answer can't depend on r is nice because you take this multiple expansion and start to calculate. There are terms that depend on r and terms that don't depend on r. Anything that depends on r you can throw away. Things might blow up if you let r go to infinity. You throw away. You no longer are sweeping them under the rug. You're throwing them away because you know they will be canceled by analogous terms from the other integral. So the rule is just in this integral, just keep the stuff that's independent of the radius of the near zones. And in this integral, just keep the stuff that's independent of the radius of the near zone and add them up. You're guaranteed that you get the radius. So this is now a much more rigorous way to take care of being able to do this kind of multiple expansion in the near zone and not have to worry about intervals that might diverge. They actually don't diverge because any divergence is canceled by similar terms coming from that other interval. But you can't, there will be stuff from this other interval that is independent of that near zone radius and that will produce physical effects. And we'll discuss what those effects are as we go along. They turn out to be very important contributions, although they are of high post-Newtonian order. They don't contribute to the leading effects, but at some point in a post-Newtonian expansion, they will contribute to the gravitational wave signal. And in fact, what they contribute is something called tails. And the basic idea is one of the things they contribute is tails. The basic idea is that, of course, when we look at this contribution to the field at our field point x, stuff coming from the multiple expansion, it's stuff that just follows retarded time. The field here is just due to the field here at this particular retarded time, t minus the distance between this zone and our field point. But that other term, those integrals over the rest of the null column, remember, involves an integral into the infinite past. And that comes about because the source might emit some gravitational field earlier than the retarded time, but that field can scatter off the curved space-time that the source itself produces. Remember, the space-time molecule is not flat, it's curved. And because gravity interacts with gravity is non-linear, so T-space can scatter basically off the curved space-time out here and reach us here today at the same time as this signal reaches us, yet it comes from an earlier time, earlier behavior of the source than retarded time. And even earlier some waves might have been emitted, go further out before being scattered, and they reach us, and so we get information from even earlier in the source all the way into the infinite past. Now, of course, you can show that as you integrate further and further in the past for this integral over W, the contributions get weaker and weaker. In fact, you can even show they diverge. But it will turn out that these things make important and measurable contributions to the gravitational wave signal from various sources. And these are called, often called tail terms. Not quite sure why they're called tail terms, but sometimes they, maybe somebody knows the origin of the term tail. Some people claim it was Bryce DeWitt, somebody up here who came up with this particular terminology. Now this calculation I've been describing is calculation of the field out here in the wave zone. So this might be where our gravitational wave detector sits. But we also want to know the motion of the source itself, right? We have to find out the equations of motion of the source in terms of the field that the source generates. Well, this doesn't help us here because this is the field way outside the source. We also need to think about what is the field inside the source, near where the matter is. What is the gravitational field there? Because that's going to tell us how the source behaves. So that involves a slightly different way of doing the calculation. Now our field point is inside the near zone, and parts of it will even be very inside the material source, but we need to look at field points within the near zone. And here we do a slightly different expansion than before, because now, instead of, before remember x prime was small compared to x, right? The integration variable was in here, but x was way up there. Now x and x prime are comparable to each other, because they're all within the same zone. So because these are comparable, we don't expand for small x prime. We expand in terms of small x minus x prime relative to t. Okay, so we do a Taylor expansion about t, with this being the Taylor expansion variable. Well, that's pretty easy. It's just again, an infinite sum, 1 over L factorial, minus 1 to the L. There's a 1 over C to the L coming from here. And then we just have time derivatives of mu multiplied by x minus x prime to the L. It's a different kind of Taylor expansion, but it will work because x and x prime are both within the near zone. So for our solution, for psi sub n, notice we're now integrating over this little mountaintop of the past null cone. That's where the null cone intersects the near zone world tube. I don't know why this PowerPoint produces this weird little gray area. There's nothing, that's just a PowerPoint glitch. I don't know why it comes out. It doesn't come out when you turn it into a PDF, it shows up here. So this is just this mountaintop peak of the past null cone. And then by doing this Taylor expansion, we convert this into a power series expansion at a fixed time t, the time that we're looking at from the behavior of the source, so t is constant, and this is the new n that we're integrating. Okay? But we do the same thing we did before. This is a finite integral over a finite zone. The result may depend on the radius of the zone. There may be terms that depend on that. But we then have to add to that an integral over the rest of the null cone. In fact, use the same change of variables that we talked about before, and do that. Add the two pieces together, and the result will be independent of the radius of the zone. And again, these terms contribute, but it turns out within the near zone, for field points in the near zone, these contribute at very high Post-Newtonian order, and almost never are relevant for almost never produce relevant effects. Okay, so this will give us, at the end of the day, our field within the near zone. We're going to need that to calculate the behavior of our source variables. Okay. So let's now think about the near zone. I want to write our source variables in a particular way that turns out to be very useful when we take this iteration of the gravitational field and look at it in a slow motion weak field approximation, and this will lead us to the Post-Newtonian approximation. So remember, our matter variables were the density, rest mass density measured in a local freely falling frame rho, the pressure measured in a local freely falling frame, the energy density epsilon. It's conventional to use an energy density per unit mass density, I'll call it capital high. And then, of course, we have the torr velocity of the fluid element, which you can also write in kind of a 3+1 language, factor of the u0, dt, d tau, and you just have then 1 and an ordinary velocity v over c. So we'll now, from now on, typically take this kind of time-space split and try to write things in a language that sort of mimics Newtonian theory, where we have time and space as their own variables. So, for example, that continuity equation, or that mass, baryon mass current, J, it had vanishing divergence. But it turns out that when you look at the characteristics of this divergence of a vector, the divergence of a vector can also be written as 1 over root minus g times the alpha with a partial derivative with respect to alpha. So if I rewrite, instead of rho, I write rho root minus g times u0, then it turns out that this continuity equation, this covariant one, can be written in terms of a very Newtonian-looking continuity equation, but in terms of this rho star variable, not the physically measured rho. This is sometimes called the conserved density, simply because it obeys a nice Newtonian-looking conservation law. This is the ordinary velocity, dx dt. This is rho star. So it's, and there should be a dot there. It's the divergence of rho star v. Okay. So this is exact. As long as baryon number is conserved, this is an exact expression. But it's written in a form that allows us to use the same rules of the road as we used before in Newtonian theory. If we use this rho star variable everywhere, then we can apply this to do things like time derivatives of fields and all kinds of other useful tools. And now we're going to sort of work our way toward the post-Newtonian approximation in the near zone. We've already assumed that fields are weak. That's part of our iteration scheme, starting from h equals 0, then first iteration, second iteration. We're also going to assume slow motions. So, for example, for the matter itself, T0j, which is proportional to rho Vj, divided by T00, which is proportional to rho, is just of order V over C. And Tjk, which is like Vj dk, also contains the pressure. That ratio is of order V over C squared. Similarly, since you might imagine that this vector gravitational potential might be generated by the vector current of the source, at least for the lowest approximation, that this ratio would also be of order V over C. Similarly, this is proportional to that, so that ratio would be of order V over C squared. So we'll assume that V over C is small compared to 1, and so our expansion will be in powers of V over C. So the question is, if we want to do this kind of approximation, how do we work out the degrees of or the accuracy of any given term to get, say, equations of motion for a system that are consistent with each other? We could solve these equations for h up to some very high order, but we don't want to waste a lot of time calculating things to higher order than we need, nor do we want to go not far enough and miss terms that we would otherwise have needed. So just want to ask, to think about, how accurately do we need to know the space-time metric, that will then tell us how accurately we need to know h, to achieve some accuracy in the motion of, say, a particle. Well, to see that, let's just go to back to our original action for geodesic. It's the integral of proper time between two space-time points. We put the metric in, so there's our Lagrangian, effective Lagrangian. And now let's expand this out component by component. And here we're assuming, as we'll see throughout in post-Newtonian theory, that if you have a system with a characteristic mass and characteristic separation r, then this quantity, dimensionless quantity g over r c squared, is of the same order as v over c squared. Why? Because for a gravitationally bound body, the kinetic energy should be comparable to the potential energy, so these are just always comparable, say, in Newtonian theory. And these will then describe the expansion parameter that we'll use in our post-Newtonian approximation, epsilon. So epsilon is proportional to v squared over c squared, or to gm over r c squared. And now, if we break this up into components, we'll have a g00 and a dt by dt, dt by dt, so we'll just have a g00 as the first term. And now g00 we know has to be 1, minus g00 has to be 1, the lowest order, that's the Minkowski metric. In the next order, we know that it has to be 1 minus 2u over c squared. Because in Newtonian theory, the Newtonian Lagrangian involves just u over c squared, the lowest order. And then there'll be some more of g00 at higher order. And we want to figure out what kind of order do we need to determine that. Let's look at the spatial part, where this is x and this is j and that's k. So we have g, gij, vi, vj. Well, at lowest order gij is the Kronecker delta, so we'll just get v squared over c squared. And then there'll be some correction, delta Gij, that's contracted with Vi and Vj. There's going to be some term like this. So this bit, U over C squared minus V over C squared, with the signs the same, you know that's the Lagrangian for Newtonian theory. And of course, we can divide by C squared, that doesn't change the Lagrangian. We can multiply by M, so we haven't changed anything. We can even add a constant to the Lagrangian, that doesn't change anything. So, forgetting everything else, this, and this to the 1/2, which converts this into a 1 and that into a half, that is the Lagrangian for Newtonian gravity. So at the very lowest order, we've recovered Newtonian theory. The question is, what do we need to do to get to go to higher orders? We need that, we need that. But we also need something else. There's the terms where this is 0 and that's J, and then the other way around. So there'll be a term that's linear in V, and then something that involves delta G0J. At lowest order, we know that's 0 because the Minkowski metric is just diagonal. There's no such term, so this is some correction to G0J that we're going to have to derive. Okay? Now, so if this stuff, if these three terms give Newtonian theory, well, let's ask, what do we need to do to get the next correction? That's of order epsilon, that's of order epsilon. Suppose we want the corrections of order epsilon squared. What do we need? Okay, so that's Newtonian theory of order epsilon compared to this constant. Well, to get terms in this equation of motion, simply for our geodesic, at order epsilon squared, we need to know G00 to order epsilon squared. So it needs to be something that might involve the square of the Newtonian potential, product of these things, who knows what, that's why it would be of order epsilon squared. This has to be of order epsilon squared. Well, we already have a factor of square root of epsilon here. This is just a single v, so that's root epsilon. But G0J, we know it's a piece of the metric, so it's got to be of order epsilon itself. It also has one spatial index. What can that index be? It has to be a v in there. This is the only spatial object of the spatial index we have. So this has got to be of order epsilon to the 3/2 at lowest order. One epsilon because it's gravity, it's got to have an m over r. And an epsilon to 1/2 because the index has to somehow be tied to a v. It's like a vector potential generated by moving matter. So that means we need to know this epsilon to the 3/2. Finally here, we need to know this epsilon squared, but this is already order epsilon, so we only need Gij to order epsilon. So to get the first post-Newtonian corrections to the motion, say, of a particle moving on a geodesic, we need G00 to order epsilon squared, G0J to this order, and Gij to that order. So we don't need to know each component of the metric. It's the same order to get the equations of motion for a test particle. So this helps guide you. You don't want to waste time doing stuff more than you need. You also don't want to miss something. You might calculate that and calculate that. If you forgot about that, you can make a mistake. So it's useful to just go through, carefully understand what you need to get the correct accuracy. But this then tells us to get that we have to do 2 iterations of the relaxed Einstein equations. Remember, the 0th iteration, h was 0, so g was just 0. Delta g was 0, it's just flat space time. The first iteration is linear in g, so that just gives us the h to order epsilon. Well, that would be fine for this. It might be fine for that, but it's certainly not fine for that. We need another power of epsilon. So we actually have to calculate h2, the second iteration of h, if we want to get all the terms we need in G00. So, but when you do that, and I'm not going to go through all the steps to calculate these higher iterations, but just sort of illustrate the results and discuss them. So 2 iterations, so we get G00, G0J, and Gij.
And the end result in general relativity is this post-Newtonian metric. So we see the Minkowski metric first, -1 delta jk. We see the Newtonian term here, 2 over c squared times u. So this and that will give us just Newtonian theory. And in the spatial part of the metric, there's a correction term that just turns out to be 2u over c squared. And you get that from just one iteration of the relaxed equations. G0j turns out to be this -4 over c cubed times uj, where uj is a vector potential. Very much like the vector potential of E and M is rho prime vj prime over x minus h prime integrated. So there's a vector piece of gravity if there's a mass current. So that we get that. And then the messy part, of course, is calculating the next components, or epsilon squared components in G00. And they turn out to include, for example, a term that's simply quadratic in U. There's u over c squared, there's u squared and c to the fourth, so there's a quadratic term in the Newtonian potential. There's a term here that's 2 time derivatives of this potential. It's called a superpotential, because x minus x prime is in the numerator, not in the denominator. Okay. And this particular term, the 2 time derivatives, is the manifestation of the retardation of the field in general relativity. It's the retardation in that flat space-time wave operator. So it gives us 2 time derivatives of this superpotential. And then there's a final potential, it's also order epsilon squared, psi, that's generated by all of the bits and pieces in the stress energy tensor of the matter. There's a piece generated by the kinetic energy within the matter, rho prime v squared. There's a piece generated by the gravitational potential within the matter itself, rho prime u prime. A piece generated by the internal energy density, and a piece generated by the pressure inside the matter. So those are potentials that just come from the matter energy, stress energy tensor. So there's the first post-Newtonian metric of general relativity. Sufficiently accurate to describe things like the perihelion advance of Mercury and other phenomena. Now it turns out that if we were looking at some alternative theory of gravity, at post-Newtonian order, you get a metric that looks very close to this, but there are some differences. The potentials are all there, but you get some numerical values here that you can parameterize by just introducing a parameter gamma. This is 1 plus 2 gamma u over c squared. And gamma will then depend on the theory of gravity you're looking at. In general relativity, gamma is 1, but in different theories it could be different from 1. And up here, for example, for minus u squared, there's a beta, another parameter whose value might depend on the theory you're looking at. And then in various other terms, there's a parameter that appears here. Each of these has a numerical parameter that could differ from theory to theory. There's a parameter there that could vary, and so on. So you get, and in some theories, there's even a potential that doesn't even appear in GR that you must incorporate. So at first post-Newtonian order, that turns out to be quite simple to compare and contrast general relativity with alternative theories, because most theories simply predict more or less the same form, but just different numerical coefficients in front of all these different parameters. And so over the years, this so-called parameterized post-Newtonian framework has been developed that characterizes a wide range of alternative theories with these arbitrary parameters. And here, just for information purposes, I'll list kind of the current limits from all a range of experiments on these parameters, just to show that the results agree very precisely with general relativity. So gamma, for example, predominantly controls things like the deflection of light and the so-called Shapiro time delay in tracking planets and spacecraft. And from measurements of deflection of light from quasars and radio sources, we know that gamma minus 1 is bounded by 2 parts in 10 to the 4, but
the best bound gamma comes from tracking the Cassini spacecraft while it was on its way to Saturn some years ago. And looking for the excess delay as the tracking signal between us and the spacecraft passed close to the sun, the curvature of space-time can cause an excess delay, and that was measured, and the limit on gamma is a few parts in 10 to the 5. Beta, it turns out, appears in the perihelion advance of Mercury, and we now found that at the level of a few parts in 10 to the 5 with modern tracking of Venus, of Mercury, and other planets. There's also an important effect that depends on beta called the Nordtvedt effect. This is a violation of the principle of equivalence, of the weak equivalence principle, but when you have gravitationally bound bodies, so it's a new effect that comes in various theories of gravity. But lunar laser ranging, as I mentioned before, shows that the Earth and the Moon fall with the same acceleration toward the Sun, even though each one contains a different fraction of gravitational binding energy. And so lunar laser ranging places an order on this combination of parameters, but that limits beta to be a few parts in 10 to the 4. There's another set of parameters that appear that are zero in general relativity, but could be non-zero in alternative theories of gravity. And these parameters have the effect of kind of violating Lorentz invariance within gravity. Again, every metric theory obeys local Lorentz invariance, but if you have gravitational systems that are moving relative to some preferred frame, there can be observable effects in various theories that can be measured, but all the evidence says there are no such effects, down to various levels of accuracy. Some using millisecond pulsar data, some using lunar laser ranging, and so on, but these all show that these parameters vanish to various accuracies in agreement with general relativity. And a final set of these parameters are non-zero in any theory of gravity, or could be non-zero in any theory of gravity that's not based on an invariant action. The thing is, virtually every theory that's invented these days uses an action as a starting point, like general relativity. You build the theory by defining the action of the theory and go to town. And in such cases, these parameters are automatically zero in any such theory. And some of them have been found to quite extraordinary precision. This alpha 3 has to be less than 4 parts in 10 to the 20. A weird effect that happens when you have spinning pulsars in theories where this is non-zero. And other bounds have been placed on these other parameters. So all consistent with general relativity, all consistent with any Lagrangian or action-based theory of gravity. Okay, so it's important to discuss alternative theories of gravity, but at least we have some confidence that at least in the post-Newtonian order, general relativity, or any theory of gravity, has to agree pretty closely with Einstein's theory in order to be viable. And if you're a fan of scalar tensor theory or Brand-Zwicky theory, the Cassini measurements, this bound on gamma, turns out to place a lower bound on the coupling constant of that theory of 40,000. The higher omega gets, the closer the theory, roughly speaking, gets to general relativity in its various predictions. Okay, so any questions, comments about that? Okay, we've derived our metric to first post-Newtonian order. It's written as a functional of the various matter variables. Those potentials involve rho and v. We don't know the behavior of rho and v yet, but they're just written sort of abstractly in terms of rho and v. But now we can impose the equations of motion. If we take the covariant ones, which we can, then plug in our post-Newtonian metric into this, and we get the post-Newtonian equations of hydrodynamics. So this will allow us to find rho, v, and so on as a function of time by solving these equations with potentials all expressed in terms of the same variables. So the first line, of course, is our old Newtonian equation of hydrodynamics, Euler's equation. Notice it's written in terms of this conserved density rho star.
And all these potentials are defined using rho star because that satisfies the continuity equation that we defined based on baryon number conservation. And so all the rules of the road, like when you have to take a time derivative of a potential, the rules of the road tell you exactly how to take that time derivative because this thing satisfies the same kind of continuity equation as in Newtonian theory. So here is just the Euler, the Newtonian part of the equations of motion that we're familiar with, and here are the various post-Newtonian terms that are incorporated. So there's, notice post-Newtonian corrections to the gradient of the pressure, stuff here to correct that, something involving the time rate of change in pressure. There's post-Newtonian correction of the gradient of the potential. But I want to point out something that's a bit, that looks kind of familiar from other realms. Here is something that has the time derivative of the vector potential, and this thing is V dotted into this antisymmetric combination of derivatives. Well, this antisymmetric combination is a vector potential, so it's like a curl of a vector potential contracted with the V. So if we define this curl of the vector potential as a kind of gravitomagnetic field, then this would be like V cross B. And if we look at this and the Newtonian potential, this is the gradient of a scalar potential plus a time derivative of a vector potential. So that's like a gravito-vector field, if you think about how electrodynamics works. Remember, the E field is the gradient of phi plus A dot. So this looks like a gravito-electric field, the gradient of phi plus V cross B. So at least some of these terms look just like electrodynamics. It's like the Lorentz force equation. With one weird twist, it's in electrodynamics, it's phi plus A dot, but there's a factor of 4 here. And here it's V cross B, but here it's actually 4 times V cross B. So there's a factor of 4 that really comes from the fact that we're talking about a tensor theory and not a vector theory. That's the main reason why there's a 4 here, not a 1. But there's a kind of an analogy between these bits of the equations and electrodynamics. In fact, especially when you're thinking about various laboratory experiments to probe gravitational interaction, it turns out you can ignore a lot of this stuff. And these turn out to be sort of dominant bits. And so it's very handy to use the kind of lore and knowledge you get from E&M to consider gravitational effects using the same intuitions, because the structure is just like the Lorentz equation from electrodynamics with a few wrinkles. Okay, so, but for example, these equations could be used to describe the structure of stars or other bodies to first post-Newtonian order, and we'll also use them to work out the motion of isolated bodies and to get their equations of motion to first post-Newtonian order. So just as we did in Newtonian theory, let's think about the n-body equations of motion for isolated systems. So we're going to make the same kinds of assumptions as I did earlier on. We'll assume bodies are small compared to typical separation, isolated, no mass flow. We're going to, in this case, going to ignore contributions that scale with the sizes of the bodies. Remember in Newtonian theory, we kept all those multiple moments. Here we're going to ignore all of that because it would just make everything very messy. So we're going to treat our bodies as so small we can ignore their multiple moment couplings and tidal couplings and so on. You could, of course, include those effects, but you pay the price in very complex equations. And I just want to focus on the relativistic corrections here. So we will simply not worry about all those multiple moment effects. And to make life simple, it turns out, it will allow us to throw away certain integrals. We'll assume that our bodies are reflection symmetric. In other words, take a given body and take any plane through the center of mass of the body is symmetric about that plane. I'm not going to assume my bodies are spherically symmetric necessarily, they don't have to be, but that they have this kind of reflection symmetry. And for a perfect fluid, that's not unreasonable. A body could be distorted into an ellipse, but an ellipse is reflection symmetric, right? So it turns out that allows us to throw away certain integrals over each body, post-Newtonian integrals that will keep things simple. As before, we define a mass of each body, but now we're going to use this conserved density, not the physically measured density. And remember, rho star is equal to rho u0 root minus g. Or in the post-Newtonian limit, it's rho times 1 plus 1/2 v squared plus 3 times u over c squared. So it's a post-Newtonian corrected expression for the density, but again, this satisfies a very nice continuity equation, which we will exploit. So each body's mass will be given by this, and it's constant, because our rules of the road say if you take the time derivative of rho star, you find that the mass is constant. We're going to define the center of mass of the body in the same way as we did in Newtonian theory. It's a simple three-dimensional integral of rho x divided by the mass. In Newtonian theory, this was completely natural. In general relativity, it's not so obvious that this is the right definition. In fact, many papers, hundreds of papers, and several books have been written on how to define, in a completely rigorous and covariant way, the center of mass of a body in general relativity. It's a huge amount of work that has been put into this with an answer that is totally inconclusive. The trouble is it's extremely difficult to define the center of mass of a body in general relativity. In a rigorous and a sort of fully covariant and pristine way. And there are many reasons for this. First, I've used rho star. Well, there are lots of different densities in general relativity. There's a density like this, there's a density that includes the internal energy of the system, there's a density that also includes the internal gravitational energy of the body. You can find all kinds of densities to weight, your location to define the center of mass. We've chosen one here simply because it's convenient, but there are many other ways to do it. If you want to do things in a very rigorous and covariant way in general relativity, you have to wonder, how do I do this integral over space? Well, first of all, it's an integral over space, and that's already not covariant. You really should integrate over some rigorously defined hypersurface that's done in a covariant way. But furthermore, this involves taking this x and adding it up, weighted by rho, to get a final answer. But in curved space-time, how do you add a vector? You don't add a vector here with the rho here to a vector there inside the body. You have to take each vector and parallel transport it to some location, and take all the other vectors and parallel transport them to the same location before you can add them. In curved space-time, you can only add vectors when they sit at the same point. And to get them to the same point, you have to parallel transport them. Well, that parallel transport depends on the metric that you're trying to find by doing all this. And so that's a very complex and messy thing to do. It can only be done in very restricted circumstances. So it's very difficult to do, and in fact, there's no unique answer. At the end of the day, though, why should one care? All you want, if you want to describe the motion of some bodies, is an object that characterizes its quote center of mass, that you can calculate and evolve with time. The main thing you care about is that the object shouldn't wander too far outside the body. Right? That wouldn't be good. You'd like your center of mass to stay somewhere inside the body. Really what you care about
is that you want to define the center of mass and have it defined in such a way that you find this motion of the center of mass. You have a way, knowing the structure of the body, to determine the location relative to that center of mass, whose motion you calculated, to somewhere on the surface, where you might be sending a radar signal to bounce off that surface as a way to determine the motion of that body. After all, we do not describe the motion of the center of mass of the Earth. In lunar laser ranging, we measure the distance between the telescope at the surface of the Earth and the reflector at the surface of the Moon. And then we use an algorithm to translate that into the center of mass. As long as that algorithm is internally consistent, the measurable quantity is the time, round-trip travel time from the telescope to the reflector and back. That's what you measure. You don't measure the center of mass, you infer it by some algorithm. So this is as good an algorithm as you can imagine, right? Because it satisfies our nice rules of the road. And so as long as we have this and have a way to get from that back to where the little reflector is, and over here to where the telescope is, and then we can convert this measurable quantity into some information about this defined center of mass, then we're safe. I mean, that's really all we care about at the end of the day. So I'm belaboring this point because time spent worrying about rigorous definitions of the center of mass, you really don't need one. You just need one that's sensible, that's simple, that makes life easy for yourself, and that allows you at the end to convert this knowledge into something that you actually measure, like the round-trip time of a radar signal, the location of the edge relative to the location to a distant quasar. These are the measurable quantities, not the location of the center of mass. Anyway, so that's enough of that preaching. Of course, we've defined it using our rho star, which is nice. So the velocity, again, our rule of the road says it's just rho star times v. So that's our PRBT. Acceleration, rho star times a, and that's our dBdt. And then for a, we plug in the Post-Newtonian equations of motion. Okay? And as before, we'll take our center of mass of our body, we'll define a little x bar, the displacement between the center of mass and the actual x that we're integrating over that we're discussing, and so we'll expand in small powers, exploiting the fact that our bodies are small compared to their separations. But as I said, we're going to throw away all kinds of higher multiple terms and only worry about effects that that don't vary as positive powers of the radii of each body. Okay? And so we'll have multiple bodies and we'll do these intervals. And I think that's something we'll do tomorrow, sort of at the 12:30 time. We will then look at that and look at the equations of motion and discover that some potentially weird effects come out of those equations of motion, but in the end those effects all completely cancel. And we'll see that general relativity satisfies a new kind of equivalence principle that is even beyond the weak equivalence principle that we talked about at the beginning. Okay? So, thank you.